Have you ever really stopped to wonder what's going on inside that laptop or phone of yours? I mean, how does a box of circuits and plastic actually think? Well, you might be surprised to find out that it all boils down to something incredibly simple. Yep, that's it. Just two numbers. Every single thing a computer does, every video you watch, every game you play, every complex problem it solves, it's all just a ridiculously long sequence of zeros and ones. It's the fundamental alphabet of the digital world.
So today, that's what we're going to do. We're going to take a journey, starting with that single bit, that tiny 0 or 1, and build our way all the way up to the complex software we use every single day. We're going to peek inside the digital mind.
So here's the plan. First, we'll crack the code on the language computers use. Then, we'll see how they keep that data safe from getting scrambled. After that, we're opening up the digital brain to see how it actually makes decisions. And finally, we'll look at the blueprint for how all that gets turned into actual software.
All right, let's dive right in. Section 1, the language of computers. You see, before a machine can do anything, it needs a way to understand information. It needs a vocabulary. One of the really clever ways they figured this out early on was with something called binary coded decimal, or BCD. The idea is actually kind of brilliant in its simplicity. Instead of trying to convert a big number like, say, 123 all at once, BCD just takes it one digit at a time. It's like translating a word letter by letter, much easier to handle. And here's exactly how it works. See, each number we use, from 0 to 9, gets its own little 4-bit binary code. So that number 123, well, it just becomes 0001 for the 1, 0010 for the 2, and 0011 for the 3. It's a super direct one-to-one mapping, which made it perfect for early computers to work with. But of course, the world isn't just numbers. What about text? For that, we use character encoding. For a long time, ASCII was the king. It used 8 bits, which gives you 256 unique symbols, more than enough for the English alphabet and your basic punctuation. But then the internet happened, and suddenly we needed a global solution. That's where Unicode comes in. By using way more bits, it can represent over 4 billion combinations. That means it can handle pretty much any character from any language on Earth. It's what makes our digital world truly global. Okay, so we've got a language, but what happens when you try to send a message using that language? How can you be sure the message that gets there is the same one you sent? This brings us to our next big challenge, securing the data. And this is a huge deal. All it takes is a tiny bit of static or interference, and a single bit can flip. A 0 becomes a 1. Suddenly, the number you sent isn't the same. The letter A might turn into a C. Your entire message can become completely meaningless. So, how in the world do you catch an error that small? Well, one of the most elegant solutions is something called a parity check. The idea is so simple but so powerful. We just tack on one extra bit to our data. We call it the parity bit. Its only job is to be a little lookout, to make sure the total number of ones in the message is either even or odd, depending on the rule we set. Let's just walk through a quick example. Let's say our original data is 10, 10, 10, 0. If you count them up, there are 3 ones. That's an odd number. Now, if we're using even parity, we need an even number of ones. Simple enough. We just add a parity bit of 1. Now, our total count of ones is 4. When the receiver gets the message, it just counts the ones. If the count is even, it says, okay, looks good. If the count is odd, it knows something went wrong, and it can ask for the data to be sent again. Pretty clever, right?
Okay, so we can represent pretty much any information, and we can send it safely. But how does a computer actually do anything with it? How does it make a decision? To understand that, we have to look inside the digital brain.
And believe it or not, the entire foundation for computer logic was laid out way back in 1854 by a guy named George Boole. He invented a whole branch of math where everything is either true or false, or for our purposes, 1 or 0. This Boolean algebra is literally the mathematical engine that runs the entire digital world. So what are the physical things that actually do this math? They're called logic gates. You can think of them as microscopic little decision makers. They take in some zeros and ones, and based on a very simple rule, they spit out a single 0 or 1 as the answer. Let's look at one of the most basic ones, the AND gate. I like to call this the all or nothing gate. It's really strict. For it to output a 1, meaning true, both input A and input B have to be 1. If either one is a 0, the output is 0. No exceptions. Now, meet its much more relaxed cousin, the OR gate. This one is the any is enough gate. It'll give you a 1 if input A is 1, or if input B is 1, or if they both are.
The only possible way to get a 0 out of this thing is if both inputs are 0. And here's the absolutely mind-blowing part. By combining billions of these simple little gates, computers can perform the most complex tasks imaginable.
So we have the language, we have a way to keep it safe, and we have the tiny little logic gates to process it. But how do you organize all of that to build something useful, like the app you're using right now? Well, that brings us to our last stop, the creation of software.
You know, building good software isn't just a bunch of people chaotically typing code. There's a plan. It's called the Software Development Lifecycle, or SDLC. The best way to think about it is like the blueprint for building a house. It's a structured set of phases that guides an idea from a napkin sketch all the way to a finished product.
And these phases make a lot of sense. First, you have analysis. You got to figure out what you're even building. Then comes the design phase, where you draw up that blueprint. After that, it's coding, where developers actually build the thing. Then comes one of the most important parts, testing, where you try your best to break it and find all the bugs. Once it's solid, you have deployment, where you release it to users. And it's never really done. The cycle continues with maintenance, which is all about fixing things and making it better over time.
Now, not everyone follows these steps in the exact same way. The classic waterfall model is like building that house. You finish the foundation completely before you start the framing. Each phase has to be done before the next one can begin. It's great when you know exactly what you want from the very beginning. But what if the project is huge and you know things are going to change? That's where something like the spiral model comes in. It's more iterative. You build a small piece, test it, learn from it, and then use that knowledge to start the next, bigger spiral. It's perfect for those massive, complex projects where you need to be flexible.
So there it is. We started with a simple 0 and 1. From that, we built a language, figured out how to secure it, designed a logical brain to process it, and even created blueprints for building massive software systems. It's an absolutely incredible tower of ideas built one on top of the other. It really just leaves you with one question, doesn't it? What's the next layer going to be?